Today I'll be talking about finding scaling laws for reinforcement learning. It's mostly based off of our latest ICLR paper about scaling laws for AlphaZero, but I made this talk a bit more technical. So it's a bit more about how you can use scaling laws for your own projects, especially for projects that involve a lot of resources, a lot of money for training a neural network. So let's start by why we need scaling laws. So if you look at old textbooks about deep learning, you will see that they treat the size of a neural network as just another hyperparameter you need to tune. So it's kind of like you have a certain, for example, data set, and you want to train on it and get the best test loss that you can. And you're going to tune all sorts of hyperparameters. And one of the hyperparameters you will tune is the size of the neural network. The problem with that is that unlike other hyperparameters, model size scales with the size of the problem. So if your data set size increases, you should expect that the model size, the optimal model size, will increase as well. So the question that drove this whole line of research is, how do we find the optimal model size when we only have money to afford one training run? When a training run, for example, like GPT-3 or GPT-4, costs millions or tens of millions of dollars. And this brings us to neural scaling laws. So this plot is from a pretty famous paper by OpenAI. And what you see here, these are three plots. They all show the test loss of a large language model, a transformer, an autoregressive transformer. It's trained to receive a bunch of words and then predict the next word in the sequence. And you can see that the test loss here in log-log scale scales like a straight line with compute dataset size or the number of neural network parameters. A straight line in log-log means it's a power law. So the test loss decreases as a power law of compute data or parameters. The important thing here is that this law, you can write it, sorry, I think it got a bit cut off, but anyways, you can write the loss as a power of either compute data or parameters with different exponents alpha. But these three laws are only applicable when you look at the regime of not being bottlenecked by the other two. So for example, if you look at test loss scaling with the number of neural network parameters, this scaling law is only applicable when you have infinite data and infinite compute. Or more realistically, when data and compute don't hinder the training of the network, only the parameters do. And I also added this plot from the technical report on GPT-4 that came out 2 days ago to show you that scaling laws are still very much in vogue. This is literally figure 1 from the technical report. The first section of their paper talks about scaling laws and talks about how GPT-4 fits to known scaling laws. They try to, what you see here is a compute scaling law. They trained what I guess is smaller versions of GPT-4 or versions with less compute, and the version with the most compute, which is GPT-4, falls exactly on this power law prediction they got from the other models. And why is this important? So this graph can show you how you can use it. This is from another very important paper from DeepMind. What I want you to focus on here is the straight black dashed line. So this line, it's another scaling law. It comes from the other 3 scaling laws I showed you in the slide before. And it basically tells you what is the number of parameters you should use given the amount of compute that you have, your compute budget. In this case, it's measured in flops, floating point operations. And you basically want to be as close as you can to this line, because when you are on this line, you perform optimally. If you're off this line, you are wasting compute on a model that is either too large or too small. And you can see that people take this to heart. So you have 3 different models here. Gopher GPT-3 and Megatron, they all fall on this line, and it's not a coincidence. They fall on this line because people try to aim to this ratio of parameters to compute. I will come back to this plot later, but let us first go forward. And so this slide is basically a summary of the take-home message of this talk. It's what you need if you want to use scaling laws for your own project. So there are basically 3 steps. First of all, you need to get the data to plot the scaling law. For that, you have to train many different models at exponentially increasing sizes by, for example, fixing the architecture of the model and increasing only the width, or increasing only the depth, or some combination of them. You need to train all models to convergence. So every model, especially the largest neural networks, have to train for long enough until they stop improving at all. And you also want to save checkpoints while you're training, and these checkpoints also have to be exponentially spaced. So for example, saving after 10 training steps, after 100 training steps, 1,000, and so on. When you have all this data, you can calculate the scaling laws, you can calculate the exponents, and then when you have that, you can extrapolate to determine the optimal size of a model for your own compute budget, which can be several orders of magnitude larger than the models you trained to calculate the scaling law. This is how you can save time and money and know exactly what is the size you need. So now I'll talk a bit about what we did. We measured the performance of AlphaZero. AlphaZero, just in one sentence, is a state-of-the-art reinforcement learning algorithm for playing turn-based games. It's uniquely known for learning not from an external data set, but completely from self-play. It just plays with itself and learns from its own mistakes and learns how to improve. It has no external data. We looked at 2 different axes, at compute and parameters, and we found at different regimes on this 2D space 3 different power laws. So the first power law we found was size scaling. We find this when we look at the limit of infinite compute. Their performance scales as a power law of the neural network size. Then when we look at an intermediate region, we get a compute scaling law where the performance of optimal agents scales as the power of the compute used to train them. And the last scaling law, and the most important one, is optimal size scaling. We see that the optimal size of a neural network scales as the power law of compute. What we did, we took, first of all, AlphaZero agents, which are made of a neural network first, and a Monte Carlo tree search. The neural network is pretty simple. We used MLPs with 3 hidden layers. They receive the state, that's the state of the game that you are playing. For example, the board game of a chessboard. And they output 2 different values. One is a value prediction, which is the probability that you will win from this state. Another one is the policy, which is a prior over the next moves. The only thing we did was change the width. We increased the width exponentially and trained different agents with different widths. When you couple this with a Monte Carlo tree search, which is an algorithm to probe future states, you get an AlphaZero agent. And we trained about 2,000 of these agents on 2 different games, Connect 4 and Pentago. So every result I will show you now is about Connect 4 and Pentago. So the first thing we saw is size scaling. Here you have 2 different plots for Connect 4 and Pentago, but they show the same thing. In both of them, we plot ELO. This is the standard metric of success, of ability to play in reinforcement learning, multi-agent reinforcement learning. And you can see that in both cases, you get a very clean logarithmic scaling of ELO with the number of neural network parameters for both games, and even with the same slope. And what this means, I will not go into this, but this is actually a power law. ELO is it's a logarithmic scale. and you can extract a scaling exponent out of it. And when you use the Bradley-Terry model, which is the underlying foundation of ELO rating, you can get a prediction for game outcome. So the expected game outcome between two players, where 0 is a loss and 1 is a win, can actually be predicted by a very simple formula. It's just 1 over 1 plus the ratio of neural network sizes times to the power of a certain exponent alpha. In this case, the exponent alpha is 0.88 or 87, and remarkably, it's the same exponent for both games. And we got the same result for other scaling laws. So the second scaling law we got is compute scaling. Here, this is it's a little bit more tricky plot. What you see here, if you focus, for example, on the Connect4 plot, it's an aggregate of training curves. So each of those colorful lines is a training curve of a single sized agent. I also color-coded the sizes of the agent. And when you plot the ELO against the amount of compute measured in floating point operations that each agent used, you can see you can trace in a red line the optimal agents. These are, it's called the Pareto front agents. These agents received the largest ELO score for their given flops value. No other agent that used the same amount of flops reached a higher ELO score. So these are, so to say, optimal agents. And these optimal agents also fit a very nice prediction for game outcome. The outcome of a game between two optimal agents only depends on the ratio of computes that they used. Again, to some power alpha C. In this case, it's about 0.55. Now, this is all, it's pretty nice, but how do you know what is the size that an agent needs to be an optimal agent? How do we know the size you need to get to this red line? And this leads us to the last scaling law and the most important one, optimal size scaling. So now we ask, how do we use these scaling laws to actually achieve optimal performance, to know which networks will achieve optimal performance? There are two ways you can go about calculating the scaling law. One, you look at each agent on the red line on the Pareto front, and you plot their sizes against the amount of compute they needed to get to the Pareto front. And as you can see, for both games, we get a straight line in log-log. A straight line in log-log is a power law, which we can use to determine the optimal size of any agent given the amount of compute we have to train them. The second approach is a bit more elegant. If you do some linear algebra, you can actually notice that the optimal size of an agent scales with an exponent that has to be determined by the other two exponents, the other two scaling laws that I've showed you. Specifically, the optimal size exponent equals to the ratio between the compute exponent and the parameters exponent. And why is this important? When you extrapolate this scaling law to much higher flops counts, you will get that this law will, we assume that it holds, it has been shown to hold for large language models and many other modalities and problems. And we can basically assume that if the problem does not change much when we increase the flops count, the amount of compute, by many orders of magnitude, we know exactly what should be the amount of compute that we use at the amount of neural network parameters that we use at much higher compute values. And I added here 2 points for AlphaGo 0 and AlphaZero. These are the state-of-the-art models trained by DeepMind to play games like Go, chess, and shogi. And you can see, for example, these two models fall way below the optimal line. It does not mean that they necessarily have to be suboptimal, because there are many lots of differences between what we did and what they did. We used a different kind of architecture, MLP instead of ResNet, and we train on Connect4 and Pentago, which are pretty different to chess and Go. But still, if you look at their papers, you can see some hint to the fact that maybe they did actually use networks that were too small for the amount of compute they had. Let me show you how. So let's look at the question, when should training stop? What I plotted here are, again, the training curves of our agents that we trained. This time it's not a log plot, it's a linear scale. And I plotted in red dots the points where the agents reach the Pareto front. So when an agent reaches one of those red dots, that means this is the point where training is optimal, and you should not go beyond that point. You could continue training beyond that point, and you would increase the ELO. Performance will increase when you train beyond that point, but it would no longer be optimal performance. If you still have compute to go further, to use more training steps and continue training beyond that point, that means you should have initially used a larger network that would have resulted in a higher performance, in a higher ELO score in this case. Now let's look at the AlphaZero paper by DeepMind. These are the training curves for chess, shogi, and Go. And as you can see here, these plots are pretty much, they converge. So they plateau at some point and they keep on training, but there isn't really much of an improvement. And this can kind of give you an indication that they wasted a lot of compute here. They could have used probably larger neural networks with the same architecture and obtained better performance on these games. There are other reasons why they might have chosen smaller networks, and one of them is, for example, inference compute. So after you train these networks on your huge compute server farm with lots of GPUs, you actually want to deploy it. You want to use it in real games. And the larger the network is, the more compute you will need it to, you will need to actually run it at test time. So this might also be a reason why they used very small networks. And the last thing I'll talk about is the dangers of using scaling laws. So we come back to this plot from the Chinchilla paper. When we first started, I told you to focus on the black line, but there are also other lines here. The other lines are the research done by DeepMind when they tried to calculate their own scaling laws. They basically redid what OpenAI did in the Kaplan et al. 2020 paper, and they reached different scaling laws. So the other three lines, which are all pretty much the same line, it's just different approaches of calculating the same thing, are very different from the black line. And the reason is they used, if I remember correctly, a different learning rate schedule, update schedule. And that was basically the only difference. And they got a different scaling law, and they proved that this scaling law is better than the original scaling law because they trained Chinchilla, which is basically a re-implementation of Gopher, where, if I'm not mistaken, the only difference was the size. They used the same amount of compute, so the smaller ran for the same amount of time, but it was smaller. And because it was smaller, it managed to run for more training runs on the same amount of compute. And it reached much better performance than Gopher. So you always have to be careful with the method in which you scale up your models. And that's it. I hope you are able to use it for your own projects now.
Thank you for that, Oren. It's pretty interesting. There was one question in the chat that popped up. So somebody asked on a previous slide, what was the vert green line after which the rules seemed to break? And that was, I think, before your optimization slide.
So which slide?
Go back. Yeah, here.
Oh, the green line. Yeah. Yeah, I glossed over that. So as you can see, this very nice linear trend goes all the way up to the green line, and then it breaks. There, it's no longer applicable. At the beginning, we didn't really know why this happens. And then we found out, you can read about it in our paper, that this is the point when the agents get close to optimal play. So because we used Connect 4 and Pentago, these are pretty small games. They're both solvable, and you have open sourced perfect solvers for these two games online. And if you match the agents against these perfect solvers, you see that they are very close in their level of play to these optimal solvers. So basically, the green line is where the agents have nowhere to improve anymore. And this is why the scaling law breaks.
Thank you. Hope that answered the question for IDOZ. Have any follow-ups, please ask. Or if anyone else has any questions, now's a good time to ask. And feel free if you want to go off mute and ask your questions, that also works. Very quiet group today. So we have one person who just joined now, so I'm like leaving a bit of time if they want to ask anything. Yeah, personally, I'm kind of curious where all this is headed. Like, I've seen that they're able to be quite successful at very complex games now, and I'm not really sure what they're trying to do next. Like, is it going to be that computer games are going to be just ridiculously immersive and everything is just going to be so interesting that people are just going to want to play games all day long?
Yeah. The problem with AlphaZero is that it was a very specific algorithm. It's just for turn-based games with open information. They've since had remarkable work on games like Stratego, for example, where you don't have open information. But the problem with reinforcement learning right now kind of seems like people always solve problems, and then you get very good algorithms at solving a specific problem, but they're not very good at solving any other problem. Unlike large language models, which right now are they're stealing the show because they can do anything. Things like GPT-3, ChatGPT, GPT-4, they can basically do a lot of different tasks, even though they were just trained on some general data. So reinforcement learning is, reinforcement learning is right now not in that position. Sadly.
I'm kind of wondering if one were to transcribe the game state into natural language, could they use one of these ChatGPT systems to figure out what's next?
Yeah, you can. I've actually seen there was a pretty hilarious attempt at playing chess with ChatGPT that I've seen recently, where each time you feed it the board position, and you ask it what's the next move should be, and it outputs always the next move, but these moves are either not optimal or sometimes they are completely illegal. And it's pretty hard. The problem is that these models right now don't really have a way to plan ahead. And AlphaZero is very powerful because it uses Monte Carlo tree search, which allows it to plan ahead. It basically, it uses a model of the game. So the algorithm knows how the game works. For example, a game of chess, it knows the rules, and it can extrapolate and predict what would be the next future moves. And the only thing the neural network does is tell the Monte Carlo tree search which moves are likely to happen because these are good moves, and which moves are not worth looking at because they're not very good moves.
That's very cool. I guess, and this is kind of creepy, but I guess everyone in the military are pretty interested in this stuff. Another question that popped up in the chat, I'm not sure if you want to speak it out loud, Edward, or shall we read it? I guess we can read it. So recently there was a new floating point representation proposed, more efficient, more energy efficient, accurate for most computations. If that new representation was used, would this always decrease the computational effort, or are there any some problems where this will not change the optimization?
Yeah, so yeah, when you have these kinds of speed up, like using floating point operations with less digits after the dot, then this can change potentially the scaling laws. Sometimes it doesn't change because, for example, if you add an additive or multiplicative improvement to performance with, let me show you, for example, this compute scaling law. If I make these agents now twice as effective at learning, so they learn twice as fast, all the agents, because I added some speed up, this will not change how the plot works. Basically, it will just shift the y-axis. It's with the y-axis, the x-axis, the flops. So the x-axis here is logarithmic, meaning if I multiply it by a constant, it will just shift. So the scaling law will remain the same, the exponent will remain the same. But it is possible, and it has been done, that people add different speed ups to the training pipeline, and then you get better models that don't fit the scaling law anymore. And then you can get a different exponent, and that's fine. You can just, after you've added this speed up, you just recalculate the scaling laws. And as we have seen, there is a good chance that the scaling law paradigm will still be applicable. So your models will still scale as the power law with resources, just with a different slope.
Very cool. Hope that answers the question.
Actually, Oren, I'm wondering, do you know what is the sort of like application of reinforcement learning for ChatGPT like models?
What do you mean?
I mean, OpenAI claims that they use reinforcement learning, right, for like ChatGPT.
Yeah.
Just wondering, like,
yes.
How exactly it was used, like
So
how exactly improves the model.
This is totally not my field, but I can tell you what I know. So they used RLHF, it's reinforcement learning from human feedback. This was, if I'm not mistaken, that was about the final stage of training ChatGPT, and it was used to align it with what humans would like to see in the output. Again, this is not my field, so everything I know is just what I've read online, but they trained a reward model from human feedback. So they literally had actual people that were sitting in front of a machine-generated content, and these people graded the content that the machine generated, and then they used this human feedback to train a reward model. So the reward model was learning to receive generated text and give it a score. A higher score it means that humans would like to see this kind of generated text, and a low score means they don't want to see it. And after they have this reward model, they used it to train ChatGPT with reinforcement learning. So now they actually have a reward signal, and like any other reinforcement learning framework, you can train an agent to maximize their reward of the generated text output.
Thank you. I see like a question about other scaling laws for meta reinforcement learning.
So what exactly is the question?
Is there scaling law for meta RL? But maybe the author of this question would like to elaborate more on this.
So as far as I know, in RL right now, the only scaling laws that I know of, at least, are there is a paper about AlphaZero by Andy Jones that does a very similar thing to what we did. He also finds scaling laws, power law scaling for AlphaZero. Even though the word power law does not appear there, it is a power law. There are some other papers that show hints that there might be scaling laws, power law scaling laws, but they don't really talk about power laws. Then there is our paper, which is a pretty extensive analysis on reinforcement learning scaling laws. And there is another recent paper by OpenAI, which talks about single agent power laws. So they show that for single agent games, you also get power law scaling laws. But these are about the only scaling laws right now for reinforcement learning, as far as I know. It's a bit hard to say for which fields we have scaling laws and for which not, because there are so many scaling laws. These scaling laws appear everywhere, in vision, in language, in reinforcement learning, across different modalities, different architectures. There are so many papers, it's a bit hard to follow, honestly.
I'm wondering, like, where the major like trend goes. Basically, now, like, the problem is that it's so expensive to train models, right? It's expensive to do, like, what do you think, like, let's say in 5 years from now, the scaling laws, where it will go, what it will look like?
I am convinced that calculating scaling laws would be the first step of any training pipeline in the future. The only reason we didn't find scaling laws until the last few years was because machine learning, deep learning was dealing with pretty small problems, and changing any hyperparameter would widely change the performance of the model. And you could kind of afford training a model several times over the same data set over and over, and it would not cost that much. Now we have reached a different regime. Now training models that cost tens of millions of dollars is actually profitable. People would want to do that. And if a training run costs $10 million, you don't want to kind of do it with hand-wavy rules. You want to know exactly what you're going to get. You want to know what is the size, what is the amount of compute, and the number of data points that you want to feed into this model to get the optimal performance. And for that, you have to use scaling laws. So yeah, I'm convinced that any big implementation, any big training of neural network models already today, it's not even the future. They have to first do some sort of analysis of how the model scales at small scale, like what we did here. The flops counts that we have here, they're pretty small. They're not that much. This is what I had. I poured the most amount of flops I had as a PhD student, but OpenAI has many orders of magnitude more than that to train GPT-4. And as you can see in their paper, they first went to the trouble of, let me go back to this plot here. So the plot here on the bottom right, they first went to the trouble of training GPT-4 on very small amounts of compute before they did this big leap forward, many orders of magnitude larger in compute, and trained the actual product that they want to release to the market.
Oren, you mentioned that, just like one last question from me. You mentioned that, like these large language models are sort of stealing, lunch, right? Stealing the breakfast. What do you think, is it possible even estimate the way research on reinforcement learning goes? When will we see the same hype around RL?
Yeah, this is more a question of personal belief, I would say. I personally believe that reinforcement learning is the future. We cannot go on just training models on data we scraped from the internet over and over. When you train on data that was generated by humans, you automatically can only at best achieve the level of a human. If you want to become better, you have to learn from your own data, which is reinforcement learning. So I personally believe eventually reinforcement learning will have its time in the sun. But right now, this is not happening. And when that will happen, I have no idea how many years that will take. No idea.